Alright, today we're going to be looking at some different basic differentiation properties. So I'm going to go through some of the basic properties with a few examples here, and then we'll go into some more practice. So the derivative of a constant function. So just any number. The derivative of a constant is 0. So in this case, we could have y equals -4. If we want to take the derivative is 0. Same thing here. We got s of t equals 45. If we want to take the derivative, it's a constant, so it's 0. Same thing here. We got f of x equals 0. 0 is still a constant, so the derivative is 0. Then we have y equals k pi over 2, where k is just some constant. So if I'm doing the derivative, some constant times pi is just a number, and dividing it by 2 is still just a number, so the derivative is 0. The single variable rule, so if I have just x, or if I have just t, or any other variable by itself, then the derivative is 1. So f of x equals x. If I do the derivative, that's just 1. S of t equals t. The derivative is just 1. X of t equals t. So x prime of t is 1. And g of u is u. So g prime of u is 1. The reason that is because of this power rule here. So the power rule, if n is a rational number, then the function x to the n is differentiable, and the derivative is n times x to the n minus 1. So if I use this first one, we got y equals x squared. So if I do the derivative, y prime, I take that exponent, pull it out front, and then I have to subtract 1 from the power. So 2 minus 1 is 1, and we usually don't write the 1. So if I go back here and think about it, if I use x, see f of x equals x. If I use the power rule, well, the exponent is 1, so bring that down, and then subtract 1 from the power. So I get 1 times x to the 0, which is just 1. So we're still using the power rule. We just have a weird case where it actually was a lot easier to just say it's the constant in front. So let's try this one here. If f of x is x to the 4th, that power rule says we bring the exponent down in front and then subtract 1 from the power. So the derivative is 4x cubed. Now this one's a little weird. I can rewrite this as, instead of square root of x, let's turn that into a rational exponent. 1/2, or power over root, right? Then I can apply that power rule and bring that exponent out front and subtract 1 from the power. So 1/2 minus 1 is actually a negative 1/2. Or we can rewrite that back in radical form. So like this. All right, same idea here. We can rewrite 1 over x as x to the negative 1 to then use the power rule. So the derivative is negative 1x, and then we're going to subtract 1 from the power still to give us negative 2. Or we could rewrite that and say that we have negative 1 over x squared. Very similarly, we can take this and make that x to the negative 2 to apply the power rule and make that negative 2x to the negative 3, or bring that back to positive exponents and make that negative 2 over x cubed. And then this last one here, we can rewrite that as x to the negative 2/3. So that when we do the derivative, we get negative 2/3 x to the negative 5/3. Because we're taking that negative 2/3 and subtracting 1, which is subtracting 3 over 3, to give us that right there. And then I could rewrite that. I could say negative 2 over 3, and I could put that back and make that cubed root of x to the 5th, or can just leave it as it is. All right, now, maybe you're asking yourself, well, all of these didn't have a number in front. We had x squared or x to the 1/2. We didn't have any numbers in front. So there's something called the general power rule, where if you only want to remember one power rule, remember this one. We still take the exponent and bring it out front. But if there is a number already there for us, then we multiply it by the number that's already there. And then we're still subtracting 1 from the exponent. So, like this first one here, we've got, if I do a derivative, I'd have 3 times 2, and subtract 1 from the power, which gives me 6x. Right? And if I do a derivative for this s of t, I would bring that 3 out and multiply it, so negative 15, and then subtract 1 from the power. Here I'm going to rewrite that as 6x to the 1/2, right? And then I can apply that power rule to do the derivative and do 6 times 1/2, and then subtract 1 from the power. 6 times 1/2 is 3, and then I can drop that back down to have a positive exponent. All right, I could rewrite this as 3x to the negative 2 so that I can do that power rule, and I would get negative 6x to the negative 3. And I can make that a positive exponent by dropping it back down. So I have 4x to the negative 1/2. So my derivative will be negative 2x to the negative 3/2. And then this one I might rewrite as negative 8x to the negative 4/3, because it's power over root. So when I do a derivative, I get negative 8 times negative 4/3 times x to the, let's see, we're subtracting 3 over 3, so negative 7/3. Well, let's simplify this out. Actually, I don't want to write or. I want to simplify that. So it's going to be 32/3 x to the negative 7/3. All right, another thing we can do is this sum and difference rule here. So if we have different pieces of functions, whether they're added or subtracted, because so far we've had just a one-term situation. So this is if we have multiple terms. So each term can be considered a different function. And if we are adding or subtracting them, we can just take the derivatives and then add or subtract them based on what we have. So like this first one, I have this one piece that's a function, and then I'm subtracting off another piece, then I'm adding another piece and subtracting another piece. So because we are just adding and subtracting them, I can just go ahead and do the derivatives individually with that power rule. And then just keep the sign in between. So this first one, we'd have 3x squared. And then I want to subtract off the derivative of the next piece, which is going to be 10x. And then I can add 2, and that's a constant. So I will leave it because it is 0. And I don't need to write plus 0. So let's do it here. So 2/5 times 5 is going to be 2x to the 4th plus 4x cubed plus 6x and plus 0. Let's do some more here. Maybe I want to rewrite that as x to the 1/3 plus 5x to the 1/2. So that my derivative will be 1/3 x to the negative 2/3 plus 5/2 x to the negative 1/2. All right, I might want to rewrite this last term for x to the negative 1 to then do a derivative. So 15 halves x to the 1/2 minus, let's see, 30 thirds, so 10 x to the, let's see, 5 thirds minus 3 thirds is 2 thirds, and then minus 4x to the negative 2. Now, I didn't have any instructions here on if I wanted positive exponents or not, and so I'm just going to leave them. But just pay attention to any instructions on anything else. Okay, let's rewrite this as, I'll just rewrite it here. So 3x squared minus 4x to the negative 2 plus 2x to the 1/2. So now let's do a derivative here. And we get 6x plus 8x to the negative 3 plus x to the negative 1/2. All right, so far we have had terms that were just added or subtracted. And right here, I have something that is being divided. So the thing is, we don't have a quotient rule yet. We will eventually. Sometimes it might be easier, though, to simplify or separate things out. So let's do a couple steps here. I'm just going to divide each term by x. So 8 x cubed divided by x plus 4x squared divided by x minus 3 over x. Let's simplify a little further because I can do a little simplifying. That's really 8x squared plus 4x minus 3x to the negative 1. So a derivative would be 16x plus 4 plus 3x to the negative 2. Okay? So those are the basic rules right now. There will be more rules to follow, but for right now, that's all we're going to do. And so now let's just do a whole bunch of mixed practice here. So we're going to differentiate each function with respect to x. All right, we have just a constant, so the derivative is 0. I can do a power rule here. So f prime of x is going to be, my gosh, I don't know what 18 times 5 is off the top of my head. Well, I know that's 40, and that would be 90. That doesn't make sense. 5 times 8 is 40, carry the 4. 5 plus 4 is 90. Okay, 90. 90x to the 17. And then we have 20x to the 4th plus 1. And then we have, let's see, power rule here, 16x to the 3rd minus 5 and plus 0. Let's see, 3 times 5 fourths is going to be 15 fourths. X to them, we're subtracting 4 over 4. So 5 minus 4 is 1. So 1/4. We can be more fractions here. Let's see, 10 twelfths. X to them, we'll subtract 3 over 3, so minus 1/3. I'm going to simplify that fraction here. So let's see, they both can be divisible by 2, so we're going to make that 5/6 x to the negative 1/3. And then we have 20 x to the negative 6. I'm going to rewrite that as 3x to the negative 3. So that'll make it what? Negative 9x to the negative 4. Do some more here. So power rule 2/3 x, and then we'll minus 1 from the power, so negative 1/3. I'm going to rewrite that as negative 2x to the 1/4. So we get negative 2/4 x to the negative 3/4, if I can write that neatly. And then I'll simplify that fraction. So negative 1/2 x to the negative 3/4. Then I have 8 thirds x cubed plus 5 plus 3x to the negative 4. And then I'll have negative, let's see, 4 times a half is 2, negative 2x to the third, plus 3 times 5 thirds is 5, and we'll subtract 1, so that'll be 2 thirds, and then plus 2. I differentiate each function with respect to the given variable. All right, so we have y equals, and then negative 3r to the 5th minus 5r squared, and we can do that with respect to r. So y prime is going to be negative 15r to the 4th minus 10r. Next one we're doing with s. I'm going to rewrite that as negative 3s to the negative 2 minus 4s to the negative 4. So that my derivative will be 6s to the negative 3 plus 16s to the negative 5. All right, a few more here. We have, let's see, derivative will be, the 2's will cancel, the 3's will cancel. It's just 1. X to the 1/2 minus, nothing fun cancels there. So 9/20 x. If we minus 5 over 5, it's going to give us a negative 2/5. I might rewrite these. Ooh. Interesting. Square root of 2 times s to the 1/3 plus square root of 2s to the 1/5. Okay, so square root of 2 divided by 3 times s to the negative 2/3 plus the square root of 2 divided by 5, s to the negative 4/5. All right, I think these are the last two here. Differentiate each function with respect to x. Problems may contain constants a, b, and c. So this is all with respect to x. So 5c, c is just a constant, so y prime is actually 0. All right, 4a, x to the 3a, we would multiply, so that would give us 12a squared, and then subtract 1 from the power, so whatever 3a is minus 1. And then we have some constants here, so then we'd have negative b, or minus b, times 3c, and then x to the 3c minus 1. I'd probably clean it up just a little bit to say, all right, 12a squared x to the 3a minus 1. I'd clean that chunk up here and make that a 3bc x to the 3c minus 1. And then maybe I'd put that in parentheses just to tell myself, all right, that 3bc is out front. All right, if you can think of any questions, let me know.